Welcome back, everyone. We are on, can you believe it, day 24 of MAT 2150. Today we are in chapters 5.3 and 5.6, continuing our discussion on applications of integration. In particular, in chapter 5.3, we will discuss improper integrals. And then in chapter 5.6, we will discuss revolved objects and their volume. Let's get right into it. First, let's consider some examples of improper integrals. We call these improper integrals because the upper bound on the integration is infinity. What that means is that we have a graph that has a horizontal asymptote. Here the horizontal asymptote must be 0. And we are asking the question, if we consider this graph towards x is going to infinity, do we capture a finite or an infinite amount of area? And what we'll do is derive a rule which tells us for these types of power functions, here the power is 1/2, here the power is 1, and here the power is 2. We're going to come up with a rule which tells us how big the power needs to be in order for these types of integrals to be finite. For our first example here, we have 1 over the square root of x. Our first step here will be to follow our definition and to rewrite our integral with the upper bound of integration equal to some letter and then to compute the limit. So we'll say this is the limit as b goes to infinity of the integral now from 1 to b of the function. We can rewrite it's 1 over square root x, which is equal to 1 over x raised to the 1/2, which we can then write as x raised to the negative 1/2. Now we can compute our integral, in a sense just ignoring this limit until the very last step. Here's how I like to think about them. Take your hand, here's my hand, and cover up that limit. We're just going to ignore that limit for the time being and only work on the integral. Now we can compute our antiderivative by applying our power rule for integration. Our power rule says if we have a power function with exponent n, then our antiderivative is given by x to the n plus 1 divided by n plus 1. So here we take negative 1/2, we add 1, and then we divide by that same number. And we evaluate that in between 1 and b. Now let's not forget, we do have this limit that we need to consider, so let's carry that notation along for the ride. Think about this notation like a motorcycle sidecar. It's the motorcycle or the integral doing most of the work, and this sidecar is just getting carried along for the ride. We need to copy it to every step in order for our problem to be complete, but we won't worry about it until we reach our destination. So again, cover up that limit. Let's worry about the evaluation. Now let's simplify first. 1 plus 1/2 gives us 1/2, or 1 minus 1/2 gives us 1/2. Divided by 1/2 gives us multiplication by 2. Now we can evaluate in between 1 and b. Again, I'm carrying our limit notation along for the ride. But we're still ignoring that limit until the very last step. Now we can bring that 2 out front. Let's do the evaluation. We get b raised to the 1/2 power minus 1 raised to the 1/2 power. Now finally, we're almost to a form where we can compute the limit. Let's simplify one more step, then we'll be able to compute our limit. We have 2 times b raised to the 1/2 minus 2. Or, if you prefer, we can rewrite it with our radical notation. That is 2 times the square root of b minus 2. Now let's think about square root of b. What will be that limit? B goes to infinity, which means its square root also keeps increasing. Infinity minus 2 is still infinity, so we get infinity. Or that this is a divergent integral. So now that we've completed our problem, I'll move the hand away so we have our nice complete notation. Notice that our limit was carried along through the entire problem. So here we had a power which was less than 1. We had a power which is equal to 1/2, less than 1. And this function captures an infinite amount of area when we consider the limit towards that horizontal asymptote of 0. Now let's increase the power. Here we have a power of 1. Will this one go to 0 fast enough at infinity in order to capture a finite amount of area? Let's first write our problem with our limit notation as the integral from 1 to b, where the limit as b goes to infinity, where we compute the limit as b goes to infinity. Now again, let's cover up this limit business. Ignore that into our very last step. Let's worry about the integration. We'll carry along in my limit like a motorcycle sidecar. The antiderivative of the 1 over x is natural log. Now we can do the evaluation. We get the natural log of b minus the natural log of 1. That gives us the limit as b goes to infinity of the natural log of b, since the natural log of 1 is equal to 0. And now we need to compute this limit. Here's where we need to think of our graph of the natural log. Looks something like this. So this arrow keeps pointing up, which means that the limit as b goes to infinity of the natural log of b is equal to positive infinity. So this is also a divergent integral, which means that it captures an infinite amount of area as we consider the integral towards this horizontal asymptote at infinity. Now let's increase the power again to 2, and let's see if we get a convergent integral this time. Step 1, let's rewrite our integral as the limit as b goes to infinity of the integral from 1 to b of x raised to the negative 2. Let's forget about that limit for a moment. Worry about the integral, but carry that limit notation through the problem. The antiderivative by our power rule, we get x to the negative 1 divided by negative 1, and we evaluate between 1 and b. Now we can do the evaluation. Let's bring this negative out front. And we get 1 over b minus 1 over 1. Let's simplify one more time. Let's distribute this negative sign to both of those terms. And let's see, we get 1 minus 1 over b. We'll think about the function 1 over x. Looks similar to the function that we have above, 1 over x squared, but doesn't go to 0 quite as fast, but still has a horizontal asymptote of 0 since it is a bottom-heavy example. So the limit goes to 0 of 1 over b, and therefore we get 1. That means that this is a convergent integral. Or we got a finite amount of area. The function goes to its horizontal asymptote of 0 fast enough so that we get finite area. Interesting. So now let's summarize these three cases. If the power is not big enough, then this type of p integral must be divergent or infinite. But if the power is big enough, then we get a convergent integral or a finite amount of area. Let's summarize that into this statement. Now we've got an idea of how big the power needs to be. Let's actually show that precisely the power needs to be bigger than 1 in order for this p integral to be finite. So now we'll follow the same steps as before. This integral will be equal to the limit as b goes to infinity of the integral from 1 to b of x raised to the minus p dx. Now we get the limit as b goes to infinity of x raised to the minus p plus 1 divided by minus p plus 1. And we evaluate in between 1 and b. Now that's equal to the limit as b goes to infinity. Let's rewrite this as x raised to the 1 minus p divided by 1 minus p. Now we can bring this constant out front. That is 1 over 1 minus p times x raised to the 1 minus p evaluated in between 1 and b. Now we can do the evaluation. We get b raised to the 1 minus p minus 1 raised to the 1 minus p, which must give us 1. And now we need to compute this limit given a few different cases. First, we have the case, what if p falls in between 0 and 1? Well, if p is less than 1, then 1 minus p is a positive number. And the limit as b goes to infinity of b raised to the 1 minus p, this is a positive number, means this has to be infinity. And hence we get a divergent integral. Now for our second case, if p is bigger than 1, then 1 minus p is a negative number. And then we get the limit as b goes to infinity of b raised to the 1 minus p is equal to the limit as b goes to infinity of 1 over p b raised to the p minus 1. Now p minus 1 must be a positive number. And so now we get that this is a bottom-heavy example, and so this must be equal to 0. And so now we can summarize. We get that this is infinity or divergent when the p falls in between 0 and 1. And let's see, what do we get in the other case? Let's come down here. Now this term goes to 0, and we have 1 over 1 minus p times negative 1, which we can rewrite with that negative 1 down here. And so that's equal to 1 over p minus 1. That's when p is bigger than 1. And now we also did the case when p was equal to 1. Then we got a natural log for our antiderivative. That also falls in the case where the integral is divergent. So now for these types of p integrals, we can just apply this rule. If the p is too small, then we get an infinite integral. If p, the power, is big enough, bigger than 1, then we know exactly what the integral evaluates to, 1 over p minus 1. Let's try a few examples now, applying this rule. Here's our rule written out, which says this p integral equals 1 over p minus 1 if the p is bigger than 1, and it's infinite if p falls in between 0 and 1. So now let's quickly evaluate each of these examples by applying this rule. For the first, we have p is equal to 4. Each of the examples, the bounds are from 1 to infinity, and we have a power function, so we can just apply this rule. P is equal to 4, therefore our answer is 1 over 4 minus 1. This integral must evaluate to 1/3, and we're done. For the next one, P is equal to 4/5. 5 is bigger than 4, which means that this is in between 0 and 1. By this rule, we get an infinite improper integral. Next, we have p is equal to 1. We already did this case carefully by hand. We can see our rule agrees. 1 is less than or equal to 1, and so this p integral has to be divergent. For the next, we have p is equal to 5 over 4. 5 is bigger than 4, so this is bigger than 1. We apply the rule, and this must be equal to 1 over 5 over 4 minus 1. Now we can simplify this. 1 over 5 over 4 minus 4 over 4. That gives us 1 over 1 over 4. Keep, change, flip and multiply. That gives us 4. So we must have a convergent integral, and it evaluates to 4. Let's try a few more slightly more complicated looking problems. But for these, we can still apply our rules. First step, let's make this thing look like a p integral. Let's bring this constant up front and rewrite this as a power function. This is x raised to the 1/2. But 1/2 is not big enough. So this must be an infinite or divergent integral. Next, let's play the same game. I see this constant can come out front. 4 divided by 9. Then we have the integral from 1 to infinity of 1 over x raised to the 5/3. Now 5 is bigger than 3, so the power is bigger than 1. Therefore we can apply our rule. Don't forget our constant out front, and we get 4 over 9 times 1 over 5/3 minus 1. Now let's clean it up and simplify. 4/9 times 1 over 5 over 3 minus 3 over 3. That gives us 4 over 9 times 1 over 2 over 3. Keep, change, flip. We'll get 4 over 9 times 3/2. Simplifying that, we get 2 over 3. So we have a convergent integral which converges to 2/3. Next, again, let's pull out this constant. We can see here that our power is 1.01. It is not much bigger than 1, but it is bigger than 1. So our rule applies. We must have a convergent integral, and we know exactly what it converges to. 1 over 1.01 minus 1. Do the subtraction, that cancels the whole number, and we're left with a decimal. 1 divided by 0.01. Let's see. Dividing by 0.01, how many decimal places is that going to move our answer over? Looks like we need to move our decimal place over by 2 places. So that will be 100 times 100. Now how many zeros will we have? 1, 2, 3, 4. So we have 1, 2, 3, 4 zeros, and we get 10,000, which is a convergent integral by our p-test. Next, we have an application of improper integrals. In our previous section, we learned that the accumulated present value of a continuous income stream is given by this expression. Here, K is the interest rate, compounded continuously, and now we're going to suppose that the money flow is to continue forever or perpetually. That means that our upper bound of integration is actually infinity. So let's compute this and actually show the formula that we get once we compute this improper integral. First, we convert this to a limit problem. We'll say the limit is b goes to infinity of the integral from 0 to b. P raised to the e, p times e raised to the minus kt, integrated with respect to t. Now we ignore our limit for the moment and compute this antiderivative. Our constant p can come out front. And we need to compute the antiderivative of e raised to the minus kt. We can either think of that as a u substitution, or we can consider its derivative. The derivative of e to the minus kt by the chain rule gives us e to the minus kt times the chain of minus k. So if we consider its antiderivative, it must be the exact inverse, which means instead of multiplication by minus k, we must have a division by minus k. That gives us our antiderivative. We get negative 1 over k times e raised to the minus kt, evaluated in between 0 and b. Now we can do the evaluation. We get the limit as b goes to infinity of p. Let's even bring this constant out front, minus 1 over k. Minus p over k now. Let's do the evaluation. We plug in b, e to the minus bt minus e to the 0. Now we can compute our limit. It might help to rewrite this. We have a negative exponent. How can we think of negative exponents? Let's rewrite it as 1 over e to the bt. E to the 0 gives us 1. Now, this is a bottom-heavy example, so this term must go to 0 as t goes to infinity. So we're left with the constant out front and the minus 1 in the parentheses, and therefore our answer is p divided by k. Let's apply this rule to an example. Here we have an accumulated present value of an investment for which there is perpetual or forever continuous money flow of $32,000 per year, and we have an interest rate of 6%. As an integral, that is the integral from 0 to infinity of 3,200 times e raised to the minus 0.06 times t dt. What that gives us, though, will just be the p, 3,200, divided by k, which is 0.06 by our rule. Now we can simplify that. Let's use a calculator. 3,200 divided by 0.06. 5, 1, 2, 3, 4 threes, and then a whole bunch more threes. So we'll say a bar for repeating. Since we have money, though, we'll round that to the nearest cent. Next, we'll move into chapter 5.6 and discuss the volume of revolved solids. The first idea we need to make peace with is coming up with volume from area. Let's think about this guy making it rain with this stack of dollar bills. Each one of those dollar bills really does have a volume, but it's a very thin slice of that paper with the cross-sectional area. And therefore, when we stack all of those together, we do end up with an object that has volume, even though each individual slice, each individual dollar bill has very thin width. And so let's come up with an integral that will tell us the volume of this object. Let's assume that we have a cube here where the length, the width, and the height are all equal to 1. What we're going to do is slice this thing into very thin strips. Very thin strip. So our strip, we took a knife or we took a saw and we cut this thing into, here's one slice. This is like one of the dollar bills that's in this stack. And so what we do is we dice up the entire thing. Each one of these little tick marks represents one of the slices that we made. We slice it thin enough, then we'll have a bunch of dollar bills, which when we lay them all together gives us the entire stack. So let's call the thickness of each of these the distance from one side to the other of each individual slice. Let's call that dx. So if we take dx and we multiply by the area, the surface area of each slice, then that gives us the volume of each slice. So the area of the face of this slice since we're assuming this is a unit cube, the height here is 1, the width here is 1, is equal to 1. And therefore the volume of each slice, when we multiply by the thickness, is 1, the area, times dx. So now if we add all of those up, in between 0 and 1, then we've gotten an integral which represents the volume of this object. Let's compute our integral and make sure that works out correctly. The antiderivative of 1 is x. And we evaluate that in between 0 and 1. We get 1 minus 0, and we get 1, the correct volume for our unit cube. Now more generally, what we've done is we've gone from A to B. We integrated the area of the slice, and we multiplied by the thickness of the slice, dx. Let's try an example here where we actually revolve an object about the x-axis. Let's first visualize that to draw ourselves a nice picture, and then compute the volume of the corresponding object. We have a constant function of 4 here. And we're supposed to start at 1 and end at 7. Now let's revolve our object about the x-axis. So here you can see here is our function. It is the straight line with height 4. Now what's going to happen when we revolve this thing around the x-axis? Revolve it around, 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 around. Now let's look from a different perspective. You can see the object that we formed is just a cylinder. We took that function, which was the straight line, and wrapped it around the x-axis. Now we want to know what is the volume of this object. Let's set that up as an integral. Starting point will be the same as before. We integrate a to b, the area of each slice multiplied by the thickness of each slice dx. Here we have a cylinder. Our cylinder starts at x is equal to 1 and ends at x is equal to 7. And we divide it up into these little slices with thickness dx and the area that we need to find. But keep in mind, we started with the function y is equal to 4 and revolve this object around the x-axis. That means our radius is equal to 4. So what is the area of each slice? Well, since it is a circle, we get that each slice has area pi r squared. So that's equal to pi times 4 squared. The radius is 4, and we get 16 pi. So now that turns our integral into the integral from 1 to 7 of the area of each slice. It's 16 pi. Multiplied by the thickness dx. Now we can integrate. This is just a constant, so we get 16 pi evaluated in between 16 pi times x. Evaluated between 1 and 7. That gives us 7 times 16 pi. Or let's simplify. Let's factor out that common constant. 16 pi out front. We get 7 minus 1. So we get 6 times 16 pi. Or 96 pi. Now let's try to generalize here. If we have just some function which defines our radius and we revolve this object or this function around the x-axis, let's say this is our function here, then we'll get some object, some revolved object Here's a cheap sketch of what this object will look like if we revolve this function around the x-axis. Then each slice forms a circle. Where the radius is determined by the function. So in general, our volume of a revolved object when we revolve around the x-axis will be given by the lower bound to the upper bound pi times our function squared, the radius squared, and then integrated with respect to x. So here's our formula for how we compute the volume of a revolved object when we revolve the function that defines the radius about the x-axis. Let's try another example, this time with a function which is not constant. Let's first try to draw a sketch of what our object will look like. Here we have the function f of x is equal to 3x, which is the straight line. And we go from 0 to 7. Now what will this look like when we revolve it around the x-axis? I don't know if it's your birthday, but we definitely have a birthday hat here laid on its side. We get this nice cone-like object when we revolve this thing around the x-axis. And so let's set up our integral. Formula is a to b pi times the radius squared integrated with respect to x. Keep in mind the radius of each slice is given by the function itself. Here our function is 3x. Our a is 0 and our b is 7. So our integral becomes the integral from 0 to 7 times pi times 3x quantity squared integrated with respect to x. Now we can evaluate. Pi can come out front. We can go ahead and square that 3. Square x, we get 0 to 7. 3 squared times x squared dx. Now 3 squared can come out front. We integrate between 0 and 7 x squared dx. The antiderivative of x squared is x cubed divided by 3. We evaluate in between 0 and 7. Let's first bring out the constant 1/3. That will cancel with one of the 3's and 3 squared. I get 3 pi times x cubed evaluated in between 0 and 7. That is 3 pi times 7 cubed minus 0 cubed. Seven cubed is 343. Times 3 gives us 1029. Let's try another example where we have the exponential function y is equal to e to the 2x. We revolve this function about the x-axis from -1 to 3. Our exponential function has a graph which looks something like this. Here. We're revolving around the x-axis. It should be somewhat symmetric. And we should get some kind of cone looking thing. Kind of looks like a megaphone. So here you are over here. Shouting into the megaphone, and your voice gets amplified out the other side. Now, at any point along our object, the function itself defines the radius. And we need to integrate from -1 to 3. So our integral from a to b of pi times f of x quantity squared dx becomes the integral from -1 to 3 of pi times e to the 2x quantity squared dx. Our pi can come out front. E to the 2x squared. Here we need to apply the power of a power rule, which says we multiply, and we get e raised to the 4x. Now we can compute our antiderivative to get 1/4 e to the 4x, and we evaluate in between -1 and 3. Bring our 1/4 out front, get e to the 12 minus e to the -4. And that one, I think we can leave just like that. If we need a decimal, we can plug it into a calculator from that point. Let's try another example, first sketching a graph of our function, and then trying our best to draw the corresponding picture of our revolved object. X squared is an upward pointing parabola. We go from 0 to 2. Revolve around the x-axis. This time we don't have a megaphone. Since it will be closed at this end, looks like we have some kind of witch's hat. So one slice here goes through the x-axis. The radius of each slice is determined by the function itself, and we integrate from 0 to 2. We integrate from 0 to 2 pi times our function squared with respect to x. We get the integral, pi times the integral from 0 to 2 of x raised to the 4th power dx. The antiderivative of x to the 4th is x to the 5th divided by 5, and we evaluate in between 0 and 2. Pi divided by 5 times 2 to the 5th minus 0 to the 5th. Two to the 5th is 32, so we'll get 32 pi over 5.